Welcome to the AI Research Roundup. I'm Alex, and today we're looking at a paper trending on X, published on July 23, 2025. This paper, published about 6 days ago, introduces a new theoretical framework to explain the performance of state-of-the-art neural networks and provide quality metrics without needing any data. The paper is titled SETOL, a Semi-Empirical Theory of Deep Learning, and the implications for how we evaluate models are pretty significant. This paper uses ideas from statistical mechanics to formalize why certain mathematical patterns appear in the layers of well-trained networks. And looking at the reactions online, it's clear the community is really intrigued by this approach. The main takeaways people are highlighting are the deep connections to physics, drawing on ideas from thermodynamics and even quantum mechanics to explain learning. There's also a lot of excitement around the idea that this gives researchers a practical, layer-wise roadmap to see how well different parts of a model have actually learned, offering a more principled way to measure quality. And the table of contents really lays out how they build their argument. They start by reviewing a concept called Heavy-Tailed Self-Regularization, or HTSR. This is an existing idea that the weights in well-trained networks show a specific statistical pattern, one with more extreme values than you might expect. From there, the authors dive into their own theory, which they call SETOL, and then connect it all to the statistical mechanics of generalization. This structure really shows how they're building from an observation to a full-blown theory. Building on that idea of heavy-tailed self-regularization, these plots show exactly what that looks like in practice. We're looking at the empirical spectral density, or ESD, for a layer in a VGG19 model. The ESD is essentially a histogram of special numbers called eigenvalues, which reveal the most important features a layer has learned. The key observation here is that for good models, the tail of this distribution follows a specific pattern, a power law. These plots show how finding the best fit for that power law is critical for the theory. This table then organizes these patterns into what are called universality classes, a term from physics for systems with similar high-level behavior. It's essentially a diagnostic chart for network layers. You can see categories from random-like, which fits a Marchenko-Pastur or MP distribution, typical for untrained layers, all the way to very heavy-tailed. The key metric is that alpha exponent. For a well-trained layer, the sweet spot is the heavy-tailed class, with an alpha between 2 and 6. This suggests the layer has learned effectively. So, to really understand that table, these plots show us what that random like Marchenko-Pastur distribution actually looks like. The chart on the left shows the theoretical shape for the eigenvalues of a random, untrained layer. You can see how the shape changes for different layer aspect ratios. The chart on the right then shows that this distribution has a very sharp edge. Anything beyond this edge, plus some tiny random wiggles known as Tracy-Whittem fluctuations, is considered a spike, a signal that the layer has learned something important, not just random noise. Alright, so how do we get from those individual eigenvalue spikes to a complete theory? This flowchart lays out the entire conceptual roadmap. It starts with a classic idea from statistical mechanics, the student-teacher model, where a student network learns from a fixed teacher, which in this case is our actual trained network layer. The goal is to calculate a layer quality metric. This involves advanced mathematical tools like the R transform, which helps describe the eigenvalue distribution. The chart shows how this path ultimately allows the authors to derive those practical heavy-tailed metrics, like alpha, from first principles. Building on that theoretical framework, these plots show us what it looks like when things go right and when they go wrong. On the left, we see a well-formed empirical spectral density from a VGG16 model. The green bars, representing the original layer, show that classic heavy-tailed shape we've been talking about, a sign of good learning. But on the right, we see a problem the authors call a correlation trap. Here, the green distribution has collapsed and looks a lot more like the random, untrained version. This diagnostic shows the layer's learning has been disrupted. So, to wrap up, this research gives us a powerful new lens for understanding deep learning. It provides a formal theory called the Semi-Empirical Theory of Learning, or SETOL, to explain why well-trained models have those special heavy-tailed eigenvalue distributions. This allows for practical, data-free diagnostics to check model quality and spot issues, like correlation traps. It's a fascinating bridge between machine learning practice and fundamental physics. That's it for this episode of the AI Research Roundup. I'm Alex. Thanks for listening.